Good morning all. I want to take another look at this. It's the supercapacitor protection board. You can see I've got one of them on each of these two 700 farad 2.5 volt capacitors. And I'm very pleased to say that this video is being sponsored by JLC PCB, manufacturers of these very high quality printed circuit boards that I made for my Knight Rider project. 10 prototype PCBs for just $2 plus postage. Because when I did a reverse engineering of this in a video a few videos ago, I missed something out. So let's add that in right away so that you can see what I missed out. And it's this. The reference pin on the TL431 is actually connected to VCC, or maybe I should call this cap positive and this cap negative, because these positive and negative lines are connected directly to the capacitor positive and negative. Now, when you look at this reference pin being connected to VCC, or cap positive, I should say, it's still not immediately obvious what this is doing. And that's because no one's ever seen a Zener diode with 3 connections. So the TL431 isn't quite a Zener diode, it's slightly different. I think to fully understand this circuit, we're going to have to look at the datasheet for the TL431. Now, I just want to say at this point, it's perhaps not surprising that I missed that little link of the TL431 reference to VCC. If you look at the big circular pad that goes around the capacitor positive with that big plus sign, run that up into the unoccupied pads, you can see that between two of those unoccupied pads there is actually a very tiny thin track. The idea is you can cut that if you want and fit a resistor in there, but if you don't cut it, of course, that reference point of the TL431, you can see it's the little SOT23 device at the top left of the board there, is actually connected directly to positive. So that's the thing I missed when I did my reverse engineering. I've added it in now, but let's take a look at this 431 datasheet. So here's the datasheet for the Texas Instruments one. They talk about the TL431. There's also a TL432. Certainly in the simplified schematic, they show it as a sort of Zener diode type thing with an additional connection coming out the side. And indeed, here in the pinouts, they certainly refer to the 3 connections as cathode, anode, and reference. But I think we need to go to page 19 and the functional block diagram to really understand how this thing works. We have here a VREF, a voltage reference. This is 2.5 volts, which goes into the negative input of what they call the amplifier. But unless you put feedback around this amplifier, it really works as a comparator. Here's the reference input pin that goes to the non-inverting input of the comparator, and here are the cathode and anode. So the way it's used on this capacitor protection board is that reference, as in my diagram here, reference, this third pin, is connected to capacitor positive. VREF is a 2.5 volt internal reference, which means that if cap positive is 2.5 volts or above, then this comparator will turn on, and this transistor will therefore turn on, and it will pull this point, the cathode, down towards the anode. Now, it can't pull the cathode voltage all the way down to the anode voltage, otherwise this device has no voltage across it and it's just going to shut down and not operate. So it doesn't actually do that. It pulls the cathode down to a certain voltage above the anode voltage. The anode, of course, here is connected to capacitor negative. Now, to see how low it pulls the cathode when this device turns on, when the internal transistor turns on, we have to go to this page, page 23. There's a waveform diagram here which shows timings for different supply resistances. But it says here, the TL431's output low level voltage in open loop comparator mode, and that's certainly the mode it's being used in in this capacitor protection circuit is about 2 volts. That's a little tilde squiggle thing. So about 2 volts. It pulls this cathode down to about 2 volts above the anode, which means that the voltage at this point is only 0.5 volts below the about 2.5 volts that's on capacitor positive. So we're charging our capacitor up. Oh, the sun's come out. It gets to about 2.5 volts. Oh, my windmill has started up. And the comparator will see that the 2.5 volts on its non-inverting input is greater than the 2.5 volt reference on its inverting input. This will switch on, the transistor will turn on, that will pull this point in the circuit down to 2 volts above, well, the cathode will be pulled down to 2 volts above the anode. That puts about half a volt across this 620 ohm resistor. Now we can calculate the current flowing through there from the half a volt and the 620 ohms, but I'm more interested in, does that give us enough base emitter voltage across this 8550 PNP transistor for it to actually start conducting and current to flow down that path, and therefore current to flow emitter collector? Well, it must, because this circuit works. So it's all a bit borderline, I think. But yes, this transistor, I mean, maybe this point pulls a little bit lower than 2 volts. Who knows? But yeah, this transistor turns on, a current flows down through the 431, another current flows through the 8550 transistor into the D882 NPN, that turns on, and current flows down through the 400 milliohm resistor and through this NPN transistor. And that, of course, is where the main discharge current is flowing to hold, because it doesn't actually discharge the capacitor, it just holds it at 2.5 volts. To hold it at 2.5 volts and to stop an amount of current flowing into the capacitor from taking its voltage above 2.5 volts. Now, we saw that the capacitor voltage does go above 2.5 volts, and it seems that the more current you force into the capacitor, the higher its voltage creeps above 2.5 volts. So this circuit is not entirely effective, but it works to a degree. So what I really need to do is force different amounts of current into the capacitor with it sitting at around 2.5 volts, and just see how much current I can push into the capacitor and have this circuit completely offset that current. In other words, completely burn it up, mainly in this transistor, before the capacitor voltage starts to rise alarmingly high. Now, it's all a bit dodgy because the capacitor does seem to rise up to, well, I think it got close to 2.6 volts when I was forcing in a reasonably high current. So I'm not quite sure how far I can push that test. But there is something else I want to do here. I feel that there may be enough voltage. When this transistor turns on fully, we should only have about 0.2 volts collector emitter. We'll have 0.6 volts across this transistor base emitter. That means we lose 0.8 from the 2.5. That means we've got 1.7 volts left here. Is that enough for me to put a red LED in there? I'm assuming the current flowing down here is not going to be sufficient to burn this LED out. We can probably go up to about 50 milliamps before it goes pop. Can I put a red LED in that path and have it used as some sort of indicator, slightly more sophisticated indicator than the one that I'm using on this board, which is simply that I've got a blue LED strapped across capacitor positive and negative? I'd like to try this out. It shouldn't be too hard, because it just so happens that the link between base of the NPN and collector of the PNP actually runs over onto the back of the board. So all I need to do is cut that track, solder an LED on the top side between base there and collector there, and we can try this out. I think I'm going to do that now. Aha, look at this. Here's another one of these protection boards where I put a blue LED across these resistors. But I mean, as we saw in the last video, very little voltage develops across these resistors, so that LED never came on. In fact, more voltage develops across this transistor. So if anywhere, I should have put that LED across collector emitter of this transistor, but that is almost the same as across capacitor positive and capacitor negative. So no, I'm going to go for this red LED in this path. So I'll use this one. I don't think this one's been adulterated. So let's adulterate it and cut that track. So hopefully this should be a relatively easy mod. Just put a cut across that track. So I'll just put 2 heavy score lines in there and then try and dig out, probably shouldn't cut towards me, dig out the copper that's sitting in that gap. I think I might do this off camera because it's going to be ugly. Right, I think that's got it. I've cut that track out. So now on the other side, I can solder an LED on this top side. I'm just going to use a regular through-hole LED. From the base of the transistor, that's that top pin there, to the top pin of the 2TY, which is the PNP transistor. And that should complete the circuit. And then we can test this sitting side by side with a regular one to see how much current I can force into the capacitor and have this circuit completely absorb it. So I'm going to take a red LED, just bend the legs out to 90 degrees or 180 degrees, I suppose. And then once I've worked out what the span is across there, I'll chop these off. I need the soldering iron to solder that onto there, and we'll give this a try. Right, so I just want to tin up NPN base here, get a bit of lead solder tinning on there, because it's probably not leaded solder on there. Oh, this is going to be tricky. Tin up the collector of this PNP. Not much to go on there. I think that's done it. And tin both legs of the LED so that I can pretty much glue this component in without applying additional solder, or not much anyway. Right, now I'm going to solder this on here. I'm not sure how well you can see this, but let's get that soldered on there. Ooh, soldering that side onto the collector of that transistor is going to be a bit more tricky. Right, there's the red LED sort of hovering between base of the big transistor and collector of the small transistor. It's kind of sitting up just off the board. Cathode side, flat side, pointing towards the base of the NPN. So that all looks good. Let's get that on one of these capacitors. Right, let's take this board off this capacitor. Ooh, I must remember my little spade terminals are on there, and they do rotate when I undo the screws, which I've got to be careful of because they kind of slide around and touch various parts of the circuit to various other parts of the circuit. So let's get those out. Right, now I can undo these, and while I'm undoing these, I just want to be careful that I don't short across here. I'm not sure what sort of residual charge there is on here, if any, but I want to take those out without them falling across the connections. So don't let them slip out of my hand. Take that off. Put this one on, check for the little positive marker there, positive on there. That fits across there. Put the bolts back in. I will need these little connection points because they fit onto the 2 diodes that are on my little power supply. So let's get these bolts on, trying not to short across the gap. Put these in part way, and then I'll slip these 2 spade terminals underneath there. Right, that's all on. I've got my red LED, so let's connect these 2 things. Positive goes to positive, negative goes into there. They're a bit loose, so what I need to do is bend these out a bit because the angle gets a bit overbent, because I want them to have a sort of friction fit on there, which they now do. Good, okay, I can start charging that. Let me get some power for this thing. Right, I've put my multimeter across the capacitor so we can see the voltage. Actually, it's just occurred to me that I was going to check the relative voltages after quite a long time. It's been about 3 days, I think, of the capacitor that has my LED on it and the capacitor that didn't. So that one's 0.98. Let's just check this one, if I can hook that onto there. This one is 1.2. So actually the one without my blue LED across it has discharged further than the one with, so certainly having that blue LED on there doesn't seem to cause additional discharging. I mean, it wouldn't, would it? Because the LED simply doesn't conduct below something in excess of 2 volts. Okay, so we've got 0.98. Let's put some power into this power supply. So I've got 3 volts there. That's what I was using last time. Current is, well, 0.5 amp at the moment. That's fine. We can just get that going, and we can watch. Well, we don't need to watch the voltage on this unit. We can watch the current because I've got voltage here. So that's up to 1 volt. I think I'm going to jack up the current now. Right, I've set this to 1 amp now. So let's switch that on. We've got 1 amp flowing. The voltage on the capacitor is coming up. The voltage on here, of course, reads a lot higher because we've got the 2 volt drops on those 2 diodes. So this is showing 1.7 on the output, but we've only got 1 volt, or nearly 1.1 on the capacitor. So I'll wait till this gets up to, I'll move that crop clip actually so that we can see that red LED. I'll reposition that and see if that red LED comes on, see if that circuit still works. Right, still got an amp of current flowing. The capacitor's up to 1.3 volts now. I've just added 2 little arrows onto my circuit diagram to show that this is an LED. I'll leave it a bit longer. While this is still charging at 1 amp, we're at 1.7 volts. Just a shout out to Dazru, who put a comment in the last reverse engineering of this protection board saying, I think you should draw the internal schematic of the TL431 to really get an understanding of the way it works. Yes, you were absolutely right. By understanding that this thing is actually a voltage reference and a comparator and a transistor which pulls the cathode down towards the anode, I have got a better understanding of how it works. Thanks for that. Capacitor up to 2 volts now. I'm watching that red LED closely because I'm kind of concerned it might suddenly come on really bright and then go pop. Another thank you, of course, to everyone who pointed out that I'd missed that tiny little track from the reference pin, and that the reference pin does indeed need to be connected to cap positive for this circuit to work at all. Thanks to all of you who suggested that. Right, still 1 amp going in, 2.25 volts. Yes, I'm thinking because of the fact that the TL431 has this open loop comparator, when the reference input goes over Vref, which is 2.5 volts, this comparator will turn on quite suddenly. That could mean that the discharge circuit comes in suddenly, although it didn't look like it was. It looked like it was more of a sort of gradual thing, more of an analogy thing, but this really is almost a digital circuit. That greater than that, that goes on. Simple as that. So yeah, I'm waiting for 2.5 volts on the cap, and very keen to see what that LED does. Right, my power supply is just flickering across from constant current to constant voltage. The voltage I've set for 3 volts at the output terminals. So now the current is going to start dropping on my power supply, but the voltage on the capacitor is continuing to go up. So at some point this protection circuit will switch on. I'm almost expecting a sort of gradual brightening up of this LED rather than an instant switch on and total fry burnout. I mean, actually, of course, the PNP transistor, this one here, will have a certain gain. I can't quite remember what the gain is, which means that whatever current I force down through its collector emitter, the current through the base emitter will be, whatever the gain is, beta times less. So I can, by regulating the current flowing down here, in other words, the current coming out of my power supply, I can potentially regulate the current flowing through that LED. Let's see if that happens in practice. Right, we're at 2.5 volts on the supercapacitor. That LED has shown no signs of coming on yet. Still got 380 milliamps flowing in to the supercapacitor. Its voltage is still creeping up, albeit incredibly slowly, but I'm still waiting for that LED to come on, because until it does, I don't believe that the protection circuit, which is now in the sun, is actually doing anything. So I'm going to let it go a little further. Right, well, this looks quite promising. The red LED does have a very dim glow now, so some current is flowing through it. That must mean that this transistor is doing something. It doesn't feel very warm at the moment, but we are at only 2.51. There is 400 milliamps still flowing into that capacitor. I'm not entirely sure where it's going. It must be going somewhere. So let's start jacking up the current, which I'll do by just pushing up the voltage in small increments, 3.1 there. So we're now pushing 530 milliamps into the capacitor. The capacitor's voltage is pushing up. Is this LED going to get any significantly brighter? Right, so at 500 milliamps, I'm now current limiting this. I've got about 2.53 volts. Let's take that up to, say, 750 milliamps or thereabouts. That's creeping up to 2.54. This doesn't seem to get noticeably brighter. There are minute changes in brightness, but you can see current flowing through that LED. Let's see if it'll offset an amp. So let's take that up to 1 amp. This is pushing ever higher. I suppose this is getting a bit brighter. It's very hard to see on camera. That's pushing up now to more like 2.56 volts. So I don't think this LED has affected the operation of the protection circuit. Is that getting warm? Yes, that is getting warm. How warm? Is it going to burn my finger? Oh, it's getting just moderately warm. I wonder how far I can push this current. 1.2 amps. This is now pushing up towards 2.58. So there does seem to be a sort of analog relationship between the amount of current you try to force in the capacitor and how far the voltage of the capacitor pushes up above its what it's supposed to be, 2.5. I mean, it's getting very close to 2.6 now, but that is 1.2 amps. Let's go to 1.5 amps if it'll do it. And this pushes ever higher. That LED is possibly a tiny bit brighter. It is holding it down, I suppose. This is presumably getting quite hot now. Oh yes, that's getting much hotter. That's hot like a radiator, so that would be about 60 degrees Celsius. Let's wind this right back down again, because I don't like this 2.5 volt capacitor being at 2.6 volts. Let's take it all the way back down to 1 amp, and that starts to drop. So yeah, I don't think my LED has significantly affected this protection circuit. It doesn't protect very effectively. It lets the capacitor go above 2.5 volts, but then it did anyway, even before I put that LED in. But yeah, I quite like that LED, because at least it shows that current is flowing into this NPN transistor, and everything seems to be working kind of as it was before. And it means that when I have my set of 8 capacitors all in series, you will see these dim little red LEDs all glowing. I quite like it. The other thing, of course, is what happens if I switch the charging circuit off. So let's switch that off. The capacitor voltage starts to fall. There's no current flowing into the capacitor. This red LED is still on because, of course, this circuit is still active because it's powered by the capacitor. So this transistor is still going to be letting a current flow down here. So we're discharging the capacitor. The question is, well, these things have sort of self-discharge at this kind of voltage, so it's going to be hard to tell where this circuit stops operating. I suppose it stops operating when that LED goes off, and where the capacitor is just internally discharging on its own. So on the way down with no charging current, we're down to just under 2.5 volts. And I think that's actually gone out now. So yeah, just under 2.5 volts, and the protection circuit effectively switches off. So yeah, I'm happy that this protection circuit still works, even including my little red LED here. It's a very useful indicator that the circuit is actually active and that this transistor is sinking current from cat plus to cat minus, thus bringing the voltage on the capacitor down. It goes up to about 2.6 volts at 1.5 amps of charge current. So when it gets to these sort of voltages, I don't think I'd want more than about 1.5 amps of charge current coming in. Now, to charge these capacitors from 0, 1.5 amps might be way too low. It might take far too long to charge these caps. What you really want to do in this project is to charge these caps very aggressively at low voltages, like 5 amps or something like that. And then as they get towards their maximum voltage, start winding that current right down so that you don't overload this balancing stroke protection circuit. It's probably more of a balance circuit than a protection circuit. I'm going to have to think about the mechanism for charging these capacitors such that I don't overwhelm these little balancing circuits. Oh, that's switched off. Well, perhaps that's fitting because I think that's all I want to do for today. Yeah, cheerio.